Welcome to the last in-person lecture for the semester. Hope you had a good semester. Have a really nice Thanksgiving this week. On Monday, I will put up there will be an online lecture, so go to the address on the syllabus and look for it on Monday. That's the last lecture next week due to the Thanksgiving break. The following week, we will have 3 lectures, but all online, and then the following week is final exams. Today we want to finish what we were talking about on vector fields. Just want to remind you that this operator here we call the del operator. So delta upside down is called del. In 2 dimensions can be written as the vector of partial derivatives, d dx, d dy, without the f on there. So if you apply this to the function f, you can say, oh, it's the gradient. So we call this the gradient operator. Right? In 3 dimensions, similarly, if we have a function of 3 variables, we can take df dx, df dy, df dz, and call that the gradient of a function of 3 variables. So the operator that operates on that we'll call the del operator, gradient operator, in 3 dimensions. For example, let's pull this here. Suppose I have a function of 2 variables, f of xy equals x squared plus xy. All right? It's straightforward. We did this at the end last time. I was just trying to review a little bit. The gradient of that can be gotten by applying the gradient operator to f. It's just df dx, df dy, the vector of partial derivatives of f. That's what we say for this function. The partial derivative of x squared plus xy with respect to x is 2x plus y, right? That's the first component. Partial that with respect to y is just x, that's the second component. So there's the gradient operator. But now when we apply it to vector fields, which are functions like this, you put in a coordinate x, y, and you get out a vector. So that's a vector field is an association with each point in the space of a vector. You put in a point x, y, and you get out this vector that can be written most generally as a function of x and y times I plus a function of x, y times j, right? The first function gives you the x component of the vector. Second component gives you, second function gives you the component for y. For vector fields, we can define the divergence of f. The divergence just means take del dot f. So if del is d dx, d dy up here, and I dot it with this 2-component vector, then it's just d dx of the first component plus d dy of the second component, right, like this. It's just df1 dx plus df2 dy. Partial first component with respect to x plus partial second component with respect to y. That's how we define the divergence of the vector field. Right. Let's try that for an example here. Suppose I have, and I can do this in higher dimensions too. Suppose, for instance, I have this function vector field in 3-dimensional space. And its first component is xz, that's the component in the I direction. The second component, x squared y, goes in the j direction, and z squared gives you the component in the k direction. So you put in a point x, y, z in 3 space and get out a vector. That's the vector field there. I wonder what its divergence is. Well, you just take del dot f is d dx of the first component plus d dy, the second component plus d dz of the third component. It's just generalized just to 3 components, right? And this actually has uses in things like fluid mechanics where the divergence can be, if you integrate the divergence over a volume, then you can get we'll talk about it later, but you can use it to evaluate the amount of fluid coming out of a source within the volume. So you integrate the amount of fluid rushing in from some sources within the solid. And so the divergence is then ddx of xz gives us z plus ddy of x squared y gives x squared plus ddz of xz squared just gives 2z. So the gradient operator applied to a function gives you a vector field, right? And the vector field is df dx I plus df dy j plus df dz k. But the divergence of a vector field then gives you back a function. In this case, 3z plus x squared. Finally, we can define the curl of a vector field if we're in 3 dimensions, only in 3 dimensions because the cross product is only defined there. The curl of a vector field in 3 dimensions is just del cross f, which means you can write it as this determinant, right? That's how we used to write the cross product. And we'll put ijk in the first row, and then del in the second row, ddx, ddy, ddz, and f its components in the third row. For this example, where the components are xz, x squared, y, and z squared, we'll put those in the third row. And then instead of multiplying these, you take ddy of this minus ddz of this, and you take the I component, right? You take I times this subdeterminant, where the subdeterminant is ddy of this minus ddz of this, and so on. And so we'll just compute it straight out of here. We've got I times taking its subdeterminant, ddy of z squared minus ddz of x squared y, that's that one. Minus j times, wipe out its row and column and take ddx of this minus ddz of this. That's what we wrote here. And finally, plus k times, take its subdeterminant, ddx of this minus ddy of that. There we go. So there's the curl. The curl is actually evaluated, for instance, in fluid mechanics and evaluating how much rotation is going on within a region. And you'll see that in some of the upcoming applications. Well, let's see. Dy of z squared is 0. Ddz of x squared y is 0 because look, there's no z in there. There's no y in there. So we just get I times 0. And then ddx of z squared is nothing but ddz of xz is x. So we've got minus x here times minus j. Gives us xj. And then ddx of x squared y gives us 2xy, and ddy of xc gives us nothing. We wind up with this vector for the curl in this example. So that's the utility of the del operator or gradient operator. You apply it to a scalar function and get the gradient. You can dot product it with a vector field in any number of dimensions and get a scalar function. And you can curl it with a vector field in 3 dimensions and get another vector field. I think they're used for various quantities in engineering and physics and so forth. This section is sort of a hodgepodge, unfortunately. It does all those things with the gradient operator. Now it moves on. I guess you could call it applications of the gradient operator. It moves on to another hodgepodge that we're going to introduce and then not talk about for a section and come back to it. We'll say, in addition to the del operator being useful for those computations, it tells you when a vector field is conservative. Think of a vector field F as force. I think that's why we use that letter. Think of conservative forces like gravity, right? Is a conservative force. It's conservative in the sense that if you go around a planet and come back to the same place, it's got the same energy it did before, right? If you go on a closed path, we're going to write that as a theorem later. But it comes out of this concept here. We'll say a vector field F is conservative on an open region if on that region it's the gradient of some function, phi. If there exists a phi such that F is its gradient, then F is said to be conservative. This is actually a really significant topic because you can use this to generalize the concept of integrable functions in Calculus 1. As you'll see as we go along here. So vector field's conservative if it's a gradient of some function phi. In that case, phi is called the potential for F. And so you can think of phi as potential energy if F is the gravitational force, for instance. All right. So that'll just be a definition. And then, if you have that definition, you can actually, and you know a field is conservative, you can actually calculate the potential for it. I wanted to do one calculation for that. Suppose, for instance, I gave you this vector field here. All right. At each point x, y, you assign the vector 2x plus y for its first component, x plus 3y squared for its second component. Right? Well, that's the vector field. I know it's conservative. I wonder what the potential is such that the gradient of that potential gives me this vector field. Well, if I know that's conservative, then I know by the definition of conservative that this is d phi dx and this is d phi dy, right? That's what the definition is. There's some function phi such that this is d phi dx and this is d phi dy is the definition. So I say the f1, the first component is d phi dx, the f2, the second component is d phi dy. And if the partial derivative of phi with respect to x is the first component, then it follows that phi is the partial integral of the first component. And if d phi dy is the second component, it follows that phi is the partial integral of the second component, this time with respect to y. So I'm going to do that integration. I'm going to say I'll integrate the first component of the vector field with respect to x, and I'll get phi back. And I'll also integrate the second component with respect to y, partial integral, and get it back. And actually, I need both of these to get the entire function because if I take partial integral of the first component with respect to x, which is 2x plus y, right? The first component is partial phi with respect to x, so I take partial integral with respect to x, trying to recover phi, and I get the integral of 2x is x squared because I'm integrating with respect to x, but it's a partial integral, so when you integrate y, you treat y as a constant, you just get xy. And then there's an arbitrary constant out of the integration, but the arbitrary constant can be a function of y because after all, y was treated as a constant within the integral. So actually the most general partial integral of 2x plus y is integrate x, treating x as the variable, get x squared, integrate y, get xy, treating x as the variable, plus an arbitrary function of y. Now we'll say that's the partial integration constant. So I don't actually know what the function is by integrating with respect to x. I know it's within an arbitrary function of y. But I also know that phi is the partial integral of the second component, here x plus 3y squared, with respect to y. So I take partial integral of that with respect to y, and I can also recover phi. Partial integral of x squared, or x plus 3y squared, the second component with respect to y. Now I treat x as a constant, right? Partial integral. Integral of x with respect to y is just xy. Integral of 3y squared with respect to y is y cubed, because y is the variable. But treat x as a constant, I get that. And then the arbitrary constant of integration there is an arbitrary function of x because I'm treating x as a constant within the partial integration. So here's the most general expression integrating the second component with respect to y is xy plus y cubed plus an arbitrary function of x. Those are all functions whose partial derivative with respect to y is x plus 3y squared. Right? Now I know from the integrating the first component that phi has to have this form, and integrating the second component, phi has to have that form. How can those be equal? If they can't be made equal, then either you made a mistake in integration or the original force F wasn't conservative. For a conservative force, this always works because by definition, it's a gradient, and you can integrate the gradient and recover, right? So if this doesn't work, either it wasn't conservative or I made a mistake. And actually, most functions, most vector fields are not conservative. And so it's, for most functions, most vector fields, if you do this integration, you won't get these to match. But for this one, we noticed that, well, let's see, x squared, that must go into h of x since it's a function of only x, and y cubed in this one must be the g of y up here. And then you can add an arbitrary constant to either of these, right? That doesn't depend on either x or y. And that's what you have is x squared plus xy plus g of y must be y cubed to make the match to within an arbitrary constant c. Now that should look like your formulation from calculus 1, where you said if you had a function that was integrable, right, all functions that had that derivative, if you said a function was a derivative and integrated it, there was an infinite number of functions that had that derivative, right? But they were all equal to within a constant. This says there's an infinite number of potentials for this conservative field, all equal to within a constant. And actually, if you were to do one-dimensional vectors, just treat this as a one-component vector and do the same kind of analysis, what you get is that calculus 1 thing. If you have a derivative, right, one component is just an ordinary derivative, integrate it and get the function within a constant. So this is a generalization of that formula in calculus 1 that says if you have a derivative, all functions that have that derivative are equal to within a constant. This is the generalization to more components. So these are all potentials for that conservative vector field. So if this is some force, this will be the potential energy. And you can pick that constant. What people do in practice, they try and pick that constant conveniently so that, like in gravity, they'll pick that constant so it's zero at infinity, something like that. If they have a mass on a spring that's oscillating back and forth, they'll try and pick C so it's zero at the equilibrium position, when the mass is at its equilibrium position, for instance. All right, now I told you there's a little bit of a hodgepodge there. That's introducing basically the del operator and some of its definitions. What we're going to do now is discuss line integrals and then come back to that. Let's see, we've done just the indefinite integral and the definite integral in calculus 1, and then we did multiple integrals here in calculus 3, and now we want to do line integrals. So we'll say the line integral can be taken along a curve. Let's do it in the plane first, and we'll say this extends naturally to more dimensions. If I take the line integral along a plane curve C, given in vector parametric form, r of t equals x of ti plus y of tj, of a function f of x, y defined on a region containing this curve C, we'll say the line integral, given this notation, integral along C of f of x, y ds, is this. So that's a definition. And I need to put a little bit more in there for it to make sense. C is supposed to be given parametrically like this. In order to say what this definition means, the idea is we partition the curve C into n subintervals, subcurves if you like, of arc lengths delta S1 through delta Sn, and that's what these delta Ks are. You take a curve in the plane, you break it up into n little pieces, and you call the length of the kth piece delta Sk. Then xk star, yk star is any point along the kth piece. And then limit n goes to infinity implies, as before, you're letting the length of the longest subinterval, in this case the longest arc length of the subpiece, go to 0 as the number of intervals goes to infinity. So that's understood in there. So a lot of books will write this differently. Limit is max delta Sk goes to 0 or something like that. It means the same thing. All right? So there's the definition of the line integral. I'm going to call this one the scalar line integral. I put a little caret in there because there's actually a second line integral called the vector line integral. That's always very confusing. You go into your science class or something, and there's this one integral that's a line integral, and there's another that's a line integral. That's because there's two different types. But the second one is actually defined in terms of the first one. I'll find out. So this will be the scalar line integral because it's of a scalar function, right? Just a real function, two real variables in this case. All right, so here's the picture. The picture makes this much better than the actual formal definition. The idea is this, you can just see that up there, I guess. When I write this, I mean, suppose I have a curve in the plane, xy plane. Right? There's a curve C, and I give it parametrically by a vector parametric function, a vector parameterization, R of t. Where R of t, here is R of A, here's R of t in general, here's R of B. The terminal point of R sweeps out the curve, and the initial point of R is at the origin. We have a, just like before, R of t is a vector valued function at the origin, whose terminal point sweeps out the curve. Now, I break the curve into n subintervals of lengths delta S1, delta S2, down to delta Sn. And then I have this surface over the top, z equals f of x, y. And at each point in an interval, I pick a point, like here's a point x1 star, y1 star in the first interval. And I'll take the height up to the surface over the curve, and I'll make a curled rectangle whose shape is the curve on the bottom extended up to a height of the surface above at xk star, yk star. So that's what I'm doing. I'm taking a curved rectangle. And same thing here in the second subinterval, this one here, I take some point x2 star, y2 star, I take the height of the surface above it here, and then I take a curved rectangle of that height and the curls along the base here. The base and the top are the same curve. And so what I've got is curved rectangles. I have the area of this one plus area of this one plus area of this one plus area of this one, n of them, and that's what this represents, right? This is the height of the curved rectangle. This is the base of the curved rectangle. Base times height gives you the area of the curved surface. And then you sum over n of those, you're adding up all these curved rectangles. That is the estimated, if you like, area below the surface over the curve. So that's what geometrically you're doing. You're estimating the area of the surface over the curve. Then you take the limit as n goes to infinity, and if this limit of this sum doesn't depend on the partition or the points you pick within the partition, we say this line integral exists, and that ought to be what we call the area of the surface below this surface equals f of x, y, and over the curve. So we'll define that to be the line integral since it seems to be significant. And then it turns out that as long as this curve down here is piecewise smooth. What does smooth mean? Hard to write out everything, it takes too long, but smooth means it has a continuous derivative. Like here's a function in calculus 1. At this point, it's not smooth. The derivative seems to be changing continuously, right? It changes a little at a time until right here, it suddenly jumps. And if you have a jump in the derivative, right where it's not continuously changing, then you can get a corner. Right? So smooth means the derivative changes continuously. You shouldn't have corners as intuitively how you think. Now that's a smooth curve. Piecewise smooth means a piecewise smooth curve is a curve that can be broken up into a finite number of pieces, put end to end, each of which piece is smooth. So you have a bunch of smooth curves put end to end. Finite number of them. That's a piecewise smooth curve. Right? That's used a lot in engineering, so you want to know that concept out of here. I won't write it all out, but we'll say, suppose this is a bunch of smooth curves put end to end, finite number of them. And the function on top, z equals f of x, y, is a continuous function. Then you can show actually that this definite integral exists. That is, this limit doesn't depend on the partition or the points you pick within there. And you can evaluate it by this really nice theorem. That says what we just said, implies that the line integral is equal to this. You can evaluate it by taking the definite integral of calculus 1 from a to b. Right, if the curve is defined t running from a to b, then you integrate from a to b dt. You're integrating along the curve. F of x, y, but x and y written as functions of t, the parametric representation of the curve, times the length of r prime of t dt. There's a nice proof of that I kind of like to do, but for lack of time, I think we better leave it out. We'll just say that to evaluate a line integral, which we know exists for a continuous function over a piecewise smooth curve, we can integrate over the values the parameter takes on, a to b, f written as a function of t through x and y times r prime of t dt. Right? So this is the notation for the line integral, and it means the limit of that sum. This is how we're going to evaluate it the rest of the semester. And actually, what's kind of nice to notation is do you remember maybe that r prime of t is actually equal to ds dt when you're moving along the curve, right? If s is the r point, r prime is actually equal to ds dt, your speed along the curve, right? And so this is just saying integral f of x y ds is f of x y ds dt dt. So it has that nice way of memorizing it. It actually ties into the proof also. So you just replace ds with ds dt dt and write x and y as functions of t, and that's all there is to this theorem if you want to memorize the theorem. We'll call that equation 1 because it's an important equation for evaluating this then. I'm going to say something else. I'm going to keep looking at it. It'll come back to me. All right. Suppose I want to evaluate now this line integral. Oh, I remember what I was going to say. I was going to say, you can think of that line integral, we said, as the area of the curtain that's sitting down below the surface above and over the curve down below. That's a nice geometric way of thinking of it, but in practice, that's not what people use it to evaluate. But for practical applications, what you want to do is actually think of f of x, y in here as a density. And you can integrate, remember in calculus 1, you can find mass of a straight rod how? Suppose this is a rod going between A and B on the x-axis. And it has density at each point, delta of x. What is its mass? Remember how to compute mass of a one-dimensional rod? It kind of gets skimmed over in the book in some ways, but the mass is just the integral of the density. You integrate along the length of the rod, A to B, delta of x dx, right? You integrate density to get mass. You think of density as the rate of change of mass as you go along that. And then we found in this course that you could, in this course and the previous application, that if you took the double integral in 2 dimensions of delta of x, y, a density function of 2 variables, the double integral of the density could get you the mass of a surface area. Triple integral over a solid of density would get you the mass of a solid. Now what we're doing here is say, suppose we have a curved rod in the plane. We can calculate its mass by integrating the density function along the curve. So this will actually be used to calculate mass along a curved rod, if you like. It's complete analogy to this one. Just you do the line integral along the curve rather than along a straight rod in one dimension. So I'll just point that out as we go along. That's an application. All right. Suppose I want to evaluate this line integral now. And these are nasty because these line integrals, due to this square root, due to the r prime thing here, what is the length of r prime? It's square root of dx dt squared plus dy dt squared, right? That's the length of r prime. R prime is dx dt dy dt, the vector. And so its length is root dx dt squared plus dy dt squared. Trying to integrate that square root in practice is usually nasty, and you usually can't do that. So what happens in these problems is in order to get one I can actually do and do the integral analytically, I have to give you a cooked example. So this is a really cooked example. And in practice, though, you can always get a computer to estimate this definite integral very accurately. So if you're integrating and finding the mass of a component of the space shuttle or something, then right, you can still evaluate it pretty accurately in the computer. But to get one we can actually do an antiderivative to evaluate this thing, I had to pick a quick example. So that's what we do here. Suppose I'm interested in integrating along the curve y equals x cubed from the origin to 1, 1. All right? This function, maybe this is the density of this curved cord or rod or something that's lying there. I wonder how much mass it has all along its length. So I parameterize this curve first. You take the simplest parameterization you can. And here's what I would suggest for that one. If y equals x cubed, just let x equal t and y equal t cubed. That's the simplest one you can do. This works with other parameterizations, but why make it harder, right? You can let x equal t to the 4th and y equal t to the 12th then, right? And that would parameterize it too, but who wants to do a harder problem? So I'll do a simple one. X equals t, y equals t cubed, parameterizes the cubic, and then t runs from 0 to 1 since x did, and that sweeps out this little arc here, this little curve. Now, what is the line integral along that curve of square root of 1 plus 9xy dx, right? The scalar line integral along this curve. Well, we're going to say by equation 1, we know that it's integral of the same square root of 1 plus 9xy, where you have to place x and y with their parametric values, t for x and t cubed for y. So it's the square root integral of square root of 1 plus 9 times t cubed, replace x and y. R prime dt, that's by equation 1 we said we would use to evaluate this. Any questions on that so far? Do this line integral along this curve. I put in the parametric values for x and y in the integral, and I replace ds with r prime dt, which you can think of as ds dt since r prime is ds dt. All right. Now, this is square root of 1 plus 9t to the 4th, but nicely, since it's a Cook problem, it happens that the length of r prime is the same, right? Square root of 1 plus 9t to the 4th. Here's how you do it. You write out the parametric curve is x equals t, y equals t cubed. So you write r of t, the vector value function that sweeps out those points, is the vector with components t times t cubed, right? So there's the vector value function that sweeps it out, or the vector parametric form of the curve. Now its derivative, you take component by component, right? So derivative t is 1, derivative t cubed is 3t squared. Then the length of that is the root sum squared. 1 squared plus 3t squared square root, which is square root 1 plus 9t to the 4th. And since I cooked the problem here, right, what I have now is integrand is the square root, so is r prime, and they cancel each other, and all I have to do, not cancel, they reinforce each other, is integrate 1 plus 9t to the 4th. Right? So that'll be the value of the line integral is now reduced to a calculus 1 problem of evaluating this integral in t. That's the power of that theorem up here, is it takes your line integral, which is defined to be the limit of the sum with delta sk. Who knows the formula for delta sk, the arc length of the k fees? It's a mess. But the theorem says you can rewrite it as an integral, as a calculus 1 integral, by just parameterizing the curve in some nice way and writing this down. All right, so now we can just evaluate this. Integral 1 is t, integral 9t to the 4th is 9t to the 5th over 5. You plug in 1 and 0, take the difference. So I like calculus 1, you get 14 fifths. All right, 5 fifths plus 9 fifths. Any questions on that one? That's evaluating a scalar line integral. Just always use this formula. Think of ds as ds dt dt, with ds dt as length of r prime. You guys don't have a whole lot of questions today for the last day of class, of in-person class. I do have a homework scheduled due on this on Monday. I have one homework scheduled tomorrow on 16.1, I guess it is. We'll leave that one where it is because it's pretty easy stuff. That's on the divergence and the curl and conservative things. I think we can make that due tomorrow. Maybe I'll put it off till Monday. But we have one due on Monday on these vector fields. I'm going to delay that at least a day or two. Because I'll probably finish this up on Monday. But now, having defined that scalar line integral, the area under the curtain kind of calculation, the area of the curtain, let's define the vector line integral. This is a second line integral. The other one was called a scalar line integral because it's an integral of a scalar function, f of x, y. The vector line integral is of a vector field, f1 of x, y, I, plus f2 of x, y, j, and you can do this in more dimensions, of course. But if you have a vector field, and you consider integrating along a curve C, given parametrically by some vector valued function r of t, t going from A to B, we're going to define it to be just the scalar line integral of f dot t ds of f dot t, where t is the unit tangent vector to the curve. So that'll be the vector line integral. You say, what good is this one? It turns out this one has lots of notation, so it's very confusing. It always confuses students because of the different notations, but this is actually how you calculate work. Here's the concept. If I have time, I don't run here doing too many concepts. Concepts are very important. They help you to remember this stuff. If I have a force and I'm pulling a wagon along a path, remember how to calculate the work that I do along that path? How do I calculate the work pulling my wagon from point A to point B? I take the work, if I pull with a constant force, it's just the force times the displacement, right? Force times, if I call this displacement vector d, you can say it's force times distance, but you don't take the whole force, you only take the component of force in the direction you're moving, right? The vertical force here on the wagon doesn't do any work, it's pushing up and down. The work done is the component of force in the direction you're moving times the displacement that you move it. So it's actually f dot d, where d is the displacement and f is the force vector. So that's the work you do moving, is force dot displacement, or a constant displacement. Then, if you've got a variable force, you have to rewrite this as an integral. And so you could say, well, it's actually integral f, well, let's write it this way. If you have a curved path that you move along, what you want to do is take, if this is your force at this point, take the component of force in the direction you're moving, and the component of force in the direction you're moving is actually f dot the unit tangent. And so f dot t is the component of force along your path, and then if you integrate that along the path, that actually gives you your work. So this is going to be, this is the component along the direction you're moving. And if you integrate that, this one will give you the work. That's going to be the application of this one. We'll call that, that's for F being a force and T being time, actually. But, I'm sorry, F being a force and moving along in space dimension for df. We'll call that the vector line integral, as this definition in terms of the scalar line integral. Right? So you take the scalar line integral of f dot the unit tangent vector along the path. Now, how can we evaluate that in a reasonable way? Well, we recall that the unit tangent vector, remember the unit tangent? It can be computed by r prime, we call that the tangent vector, divided by its length. Right? If you take a tangent vector and divide it by how long it is, you get a unit vector in that direction. So here's the unit tangent as I move along the curve. And so the line integral has this notation, means this, that's the definition. But from our formula 1, this scalar line integral, ds can be replaced with r prime of t dt. So now it means this, it's f dot t, length of r prime dt from A to B. And now you say, unit tangent is actually r prime over length of r prime. I wrote up the in there a little bit. The dt here, dt. And the r prime, the length of r prime on the bottom cancels the length of r prime on the top, and what you get is just f dot r prime dt. That's the proof of this nice theorem that tells you how to evaluate a vector line integral. This is a theorem that says the vector line integral is actually evaluated along a smooth curve within with a continuous vector field here f, piecewise smooth curve with continuous vector field f, by integrating along the path from a to b. That's the parametric t limits of the vector field f dot r prime dt. It's nothing more than that. So you can think of it. This is the way you can memorize this one easily. To evaluate f dot dr, which means the scalar line integral of f dot t ds, you just replace dr with dr dt dt. That's all you do. So this thing can be evaluated by writing dr as dr dt dt and going between the endpoints a and b. That's an easy way to remember it, right? But the proof is a little more to it. Here's an example of evaluating a vector line integral. All right, suppose I have this, a path swept out by this vector value function. R of t equals t I plus t squared j. What am I doing? I've written parametric equations for this parabola, y equals x squared, right? Because you put x equals t into here, you get y equals x squared, eliminating the parameter. So there's what I'm trying to do. I'm going to move along this parabola, y equals x squared from 0, 0 to 1, 1, by this vector parametric form, r of t equals ti plus t squared j, t running from 0 to 1. Now suppose I have this vector field which has components x squared in the I direction, y squared in the j direction. And I want to calculate maybe my work done as I move along this curve here with this force field in place. Right? Then I calculate integral f dot dr, the vector line. So integral f dot dr means the vector line integral, but integral f of x, y ds means the scalar line integral. When you see this, it means a scalar line integral because you're integrating a scalar function. You see a vector field here, this is the vector line integral, and you evaluate with formula 2. So use formula 1 for the scalar line integral, use formula 2 for the vector line integral. And now, by our formula here, all we have to do to integrate f dot dr is to replace dr with, I'm forgetting my arrows, dr dt dt, and put the endpoints that t goes over, 0 to 1. All right. Well, that's the integral from 0 to 1 of f. Well, f is x squared, y squared as components, where x is t, so x squared is t squared, and y is t squared, so y squared is t to the 4th. All right, so I put x is equal to t, and here's my vector field, and then x squared is t squared, and y squared is t to the 4th. That f then has to, written in terms of t, then has to be dotted with dr dt, where here's r prime to move along the curve, is ti plus t squared j moved along the curve. Its derivative has components 1, 2t, right? So I'm going to integrate this dot this. What an easy calculus 1 integral, right? T squared times 1 is t squared, t to the 4th times 2t is 2t to the 5th. I just have to integrate from 0 to 1, t squared plus 2t to the 5th, and I'll have the work that I did along this path done by this force, right? Well, let's see. Integral of t squared is t cubed over 3. Integral of 2t to the 5th is t to the 6th over 3. Plug in 1 and 0, take the difference. I get 2/3. I do 2/3 joules or whatever the unit of work is you're using for that particular problem. There's how you can evaluate a vector line integral. I'll try and give you at least another example of that for next time. Any questions on those? It's quite a lot of material, actually. This is always a hard course to finish. And shorter lectures this semester, it's even harder. Well, that'll do it then. Again, on Monday, show up for lecture online, not here. Thank you so much for your presence all this semester. And you'll have a really nice Thanksgiving with your families or wherever you can go. I know some of you can't go over going on. So, best wishes to all of you. I'll hopefully see you online. Remember, if you come on for my office hours, use the address that's on the syllabus for office hours, not the address that's on here for class. There's two different addresses, one for office hours, one for class. But see you online soon, hopefully.